we studied instability, but next is what happens when nonlinearity kicks in and when it starts taking over and do things. So, one thing we discussed already, well, at least I hinted that nonlinearity will saturate the growth. So, things cannot keep growing, exponentially. Energy can't keep coming in fact temperature can't keep growing, it will melt. So, nonlinearity comes and saturates. So, we will see this through Lorentz equation. So, I am going to derive Lorentz equation, but my normalization is not like Lorentz, derivation is quite different. Again Crea-Haring I will use. So, but the equations are same with apart from factors, okay, so it is not normalized in the same way as Lorentz. So, we will study nonlinear saturation using Lorentz equation, which is simplest derivation for nonlinear interactions, and this for Rayleigh-Benard. So, no rotation, no magnetic field, just Rayleigh-Benard. Okay. So, before I go to discuss Lorentz, I need this interaction u dot grad theta. No, that nonlinear term was u dot grad theta. An interaction is via that u dot grad theta, and we need to write it in Fourier, like we wrote for u dot grad u. So, there was all these exercises, homework was done. Now, we need to do the same thing for u naught grad theta. So, I am just going to show you how to do this, and I will do it right now for Lorentz. So, for u equation remain the same, there are new terms like Rayleigh, Prandtl, theta, z hat, viscous term, but nonlinear term is the same thing as before. So, we need to worry about what happens for scalar. So, scalar nonlinear term is u dot grad theta, and these are linear terms u dot and Laplacian theta so Cg. So, in Fourier u dot grad theta will become what? So, you see is incompressible fluid still. So, I write this as del j uj theta, right, del j uj can go inside. So, exactly same, uj gives you ikj and uj gives you uj of q vector and theta p convolution, okay, and of kj uj is dot product. So, this is that uk and this is theta p. I take it to the right hand side, so that is why there is a minus sign. So, it is exactly same, except earlier if you recall this was u vector up, but instead of up I have theta p. In fact, it is simpler, it is one of them is a scalar. Okay. So, this is my nonlinear term, and the linear terms are straightforward. Uz will give you uz of k, and this one will give minus, okay, there is no PR. So, sorry, this one is not correct, k squared theta k, fine. So, we need to compute this for a triad interaction, the way we did for u dot grad u, so it was I k dot uq up. Now, I have I k dot uq theta p. Okay. Now, so for a triad we will use our notation will be use as k prime plus p plus q equal to 0. So, they are symmetric. So, k prime is minus p minus q. So, theta k prime will, so the convolution becomes rather convolution becomes sum in Fourier space, and sum has only two terms now, because for a triad right hand side will be involving only two terms. So, this one is q and minus p, because see there is a minus minus here, okay. So, this one nonlinear is only this, is very similar to what we did for before. Now, so this is that trick. Now, if you want to use Crea-Haring, then you have to, well, for theta there is no theta, what is Crea-Haring? Theta is a scalar. So, there is no need of Crea-Haring, there is a number sitting at the wave number k, there is a wave number k, and there is a u theta, the theta of k is a scalar. reality condition tells you that here it will be theta star of minus theta minus k will be theta star of k. Okay. So, you do not need Cray Herring for this, but this part can be still solved by Cray Herring, but for today's discussion I will not. I use my code. I will tell you what I did with my code, but that I will demonstrate later how to use it. Yes. Okay, so Lorentz equation. So, we go to derive the Lorentz equation. So, Lorentz way back in 1962 or I think long back, he took the Rayleigh-Benard equation and he kept 3 terms, 3 modes, 3 Fourier modes. So, what are the 3 Fourier modes? I forgot the 4 sign here, 4 here. So, 4u11. So, velocity field must be incompressible. So, this will give you incompressible. So, this in fact we have seen it before, sin x cos z, cos x sin z, and is it satisfying the free slip boundary condition? So, free slip will be, so there are walls along z direction. Huh? So, it is the same thing what I did for instability. I do not want to disturb my earlier analysis. So, the wall here and wall here. So, the vertical velocity must be 0 at the wall. So, vertical velocity is uz, it is 0 at z equal to 0 and z equal to pi. My box is pi pi, not now I am making my shift. So, to make my calculation simpler, I chose a box with pi pi, not 1 in vertical direction, otherwise I will have pi sitting here. Okay. So, I did not want to keep that. Now, in the sideways also I put a pi box. So, here my ux must be 0 at both these walls. So, ux, the sin x will become 0 at x equal to 0 and x equal to pi, and it satisfies this boundary condition dx dz equal to 0 and duz dx 0 at the walls, okay, at walls. So, you can check easily. So, this is a free slip boundary condition, it satisfies the free slip boundary condition. Now, temperature is 0 at the plates, temperature fluctuation. So, I remove T conduction, remember. So, this temperature is T bottom, T hot. So, there is a linear conduction profile for conduction state. So, theta is a fluctuation over it. So, theta is 0 at the plates for conducting plates. So, it is 0 at the top and bottom, and so these are, you are already familiar with this, right. So, primary mode is 1 mode, kx and kz, ky is 0. So, I am not writing ky, still a 2D system, but we have done this 1 and theta 1 and u11 before. So, this was the mode which was excited, but it was what it derived was for kc equal to pi by root 2 and kz pi, but I have changed it. I am not using those wave numbers, but well, it does not matter. So, if you look at Rayleigh critical, it is this, right. Rayleigh critical was this function of kc. So, my k is equal to kx equal to 1, kz, well, this was for Rayleigh critical versus k perp. So, I am using k perp as 1. So, this was pi by root 2. What is pi by root 2? Is 3 by 1.4 is I think around 2 with 2.02 something, okay. And so, I am somewhere here, my k perp is 1, okay. And Rayleigh critical will be a different, well, in fact we will compute Rayleigh critical. What is Rayleigh critical for this problem, for this 1 box? So, we had the formula, no. So, I am going to erase this. So, what is the formula for Rayleigh critical? So, Rayleigh critical is k power 6 by k perp square. So, what is k for the primary mode? Square root 2, right. So, kx is 1, ky is 1, so k is square root 2. So, what is k power 6? 2 cube is 8 and k per k perp is kx, kx is 1. So, my relative critical is 8. Okay, so this is what is a nice round off number, is not 657. So, I am getting rid of pi's and so on. Okay, this is for convenience. Now, so these were the modes which would be get excited for this box. So, there is also an illustration that you will not get 657 for all boxes. For this box, a Rayleigh critical of 8, onset convection will start. Now, in addition to the primary modes, which is 1 1 1 mode, I am having another mode called theta 02, and theta 02 will be sin 2z, because there is no x dependence, 0. So, cos of 0 is 1. So, it is sin 2z. It has to be sin 2z because it has to be 0 at the walls, it can't be cos 2z. Okay. Now, what are the Fourier modes present in the system? So, they will be corresponding to 1 1, there are 4 combinations, plus minus 1 plus minus 1, and there is one coming from 0 2. So, 0 2 and 0 minus 2, and in fact, why 0 2? Why not something else? In fact, so let us look at the picture. So, let me first list the numbers 0 2, it will become obvious in a minute. Okay, I am drawing the picture. So, given these, I can compute ux, uy and theta, right. This we did it before. So, this 4, you bring 4 here, write 2 sin x as e to the power ix minus ix. So, this we have done it before. So, I am looking at this mode 1 1, minus 1 1 and 0 minus 2. Okay, I just compute amplitudes for these modes. So, you can easily do it from this formula, that it will be u11 by I. Shall I do for one of them? It is straightforward. Can everybody see u11 by I? Yes or no? So, this has e to the power ix and this was e to the power iz, and the coefficient is u11 by I, because sin x gives you 1 by I. So, this we have done it before. Okay, I am following the same theme. This course is structured like that. So, if you follow the earlier part, you will do well in later parts. And uy is, because of minus sign, you get minus u11. So, ux and uy are related, and it better be, because incompressible condition, k dot uk must be 0, and u2 also, well, I am coming to u2 in a minute. Okay, and theta it will come from here, and 0 minus 2 is basically has 0, well, no velocity component, because there is nothing called u02. In fact, u02 must be 0. You know why? Because incompressible condition. In fact, u02 will have, so this is incompressible condition, it has to be 0. Okay, so this you show it yourself. Okay, this has to be 0, and Lorentz does not use u02. In fact, it has to be 0. Okay, anyways, if you want to see this is u02, the x component. So, I have to multiply this by 0, because kx is 0, then u02 z component multiplied by 2, kz is 2, this must be 0, because k dot uk must be 0. So, this is 0 anyway, so u02 must be 0. So, this is this 0. Okay. In what? Okay, so there is, you are saying u02 x, this can be non-zero.
In the table
uy. Okay, you are right. This is uz. Thank you. Yeah, so this is uz. Okay, so this is what we chose. Lorentz chose it, apart from pi's and so on. Okay. Now let's look at the. So why did I choose these three modes like this? They form a triad, right? 1 minus 1 add to 0, and you look at the z component is also 0. My ui is 0, so I did not want to write ui. So kx kz, that is our notation. So they form a triad, and triad can interact and pass on energy. So 1 1 is trying to grow, but 0 2 will take the energy. So 0 2 is okay, this is a new mode which is being generated. So that is the idea. So now So, my triads, so this is 1 1 mode, so this did not come out well, 1 1 here, minus 1 1, so this is 1 1, no, so this is x axis, y axis 1 1, this is minus 1 1 and this is 0 2, 0 minus 2, sorry, I should say 0 minus 2. So, this is the triad, so this is triangle complete, 1 1, this minus 1, x component is negative, z component is positive, this is minus 1 1, correct. So, minus 1 1 will be like that, I just shifted it, and 0 minus 2 is like this. Now, I want to do Crea-Haring, so I need to get my n hat and z hat and so on. So, choose my n hat along z direction. So, I am not trying to follow this notation that okay q cross p is n hat. Okay. So, we deviate because we will do more complex problem with this. So, let us follow this notation for n hat is z hat. So, the technology which we developed before, I am not using them right now for this problem, like 2D sin x, it was very nice, sin alpha, sin gamma, but I am not using it here. So, what is let us say for 1 1 what is E1? So, k cross n, so k is in that direction, k cross n will be towards I mean going above the paper, rather going upward like that, coming out of the paper, and E3 cross E1 will give you E2. So, E2 is that direction. So, this one is right. For this guy minus 1 1, so k cross n is into the plane, and so E2 is not to the right, E2 is to the left. Okay, so, this is a difficulty. So, that circular thing is not working because of this n hat has a difference. Anyway, my computer program generates them. Okay, so they generates E2 and it does all the calculation. So, this simple SimPy it gives you that E1 E2. So, E2 for this vector is that. Okay. So, what I need is E2 because E1 there is no component, well you can look at this, the velocity field is in xz plane, right, xz plane. So, U1 has along y direction, in fact y minus y direction, this is x, y must be into the board or into the paper. So, there is no component of velocity field along y. So, Ui is 0, so U1 is 0. So, for all these fields I can say U1 is 0. Well, I have only one mode, well 2 modes, 1 1 and minus 1 1, and they are complex conjugate or negative counterpart. There is minus, so there is another triad minus 1 and 1 minus 1, fine. So, let us work. So, if you can do it for one triad and you will get equation of motion, you do not need to work for both the triads. So, you work for this triad and solve the nonlinear term, full nonlinear equation. We need to do that because there is a coupling now. In linear stability analysis, there was no other mode to couple. So, there was 1 1 mode, but well there was minus 1 mode as well, but they were not coupled. It was not able to pass energy, but now it can pass energy. So, the triad is clear, and that is why Lorentz chooses this triad. This is by choice, necessity. Okay, now let's proceed. So, I am going to work out for nonlinear the equation for theta 0 2. So, we have the same triad again. So, I have this equation, well I need to have both of them, right. So, this I wrote it before. So, this is k, I am going to call it k prime. So, this is, you should use k prime p q, cyclic notation. I follow the same notation, but so if I am working for this, then I will have to worry about in the right hand side this p q, and there is of course uz and p r k prime. Now, if I have focused on 0 2, what is uz for 0 2? 0. I said there is no velocity field for 0 2. So, this term is gone. Now, this term is straightforward. What is k prime squared for 0 2? 0 minus 2, this is minus 2, sorry, is just 4, k square plus ky square, kz squared is just 4. this is 4. Okay, so linear term is easy, minus 4 theta k prime. Now nonlinear term, now this is what my computer program gives you. So it's best idea to, instead of writing this as minus q, you write as complex conjugate of so what are, so this p and this q. Okay, so k prime dot u star of minus q. So u star sorry u of minus q, that is u star of q, u star of minus 1 1, which is there in the table, and theta minus p is theta star of p. So theta star of 1 1, and same thing will, well, other thing is just reversed, u of minus p, so that becomes u star of 1 1 and theta of minus 1 1. So they are just, you can see they are just cross. Okay, one becomes PQ QP and then PQ. So k cross, no, I agree. Fortunately for 0 minus 2, well, true. So here you can choose yourself. So if there is no not given, well, even I am choosing in that direction, it is not going to contradict. So it is not defined, but you can choose. It turns out for this problem I do not need E2 for minus 2, because velocity field is 0 for u of minus 2. So u2 is, there is no velocity for 0 minus 2, there is neither E1 component nor u2 component. So you can choose either way, but if I were to choose it, then I will choose in that direction, consistent with other modes. Okay. So now from the table I can just plug in the numbers. In fact, you can do by hand. This problem can be done by hand. So the linear term, which is, as I said, minus 4 p r theta 0 2. Now remember, these are 0 minus 2. So the typos. So theta 0 minus 2 is theta 0 2 by I. This one is theta 0 2 by I minus. Now you can look at your notes. I will not go back. So you now start plugging in from the table. So there will be cancellation of i's, and you will get real equation for theta 0 2 is real number. It better be real, because my velocity field was theta 0 2 sin z, and temperature is real field. Similarly, u11 and theta 11 are real. Okay. So if I plug that in, then I will get, so you see I put it here, this is a time varying field, and I get this. So there will be i's will cancel, and so this is what my computer program gives you, but you can do it by hand. And this is what I get, theta 0 2 is 4 1 u11 theta 11. So this is, well, okay, this is a diffusion term and this is a nonlinear term. If nonlinear term was absent, then what happens to theta 0 2? It will decay to 0. Okay. So that is one thing, that even if nonlinearity is off, this mode will go to 0. Okay. Now this for one mode. Now we have to do for 3 modes. So 1 1 as well as so temperature theta 1 1, and I do not need theta minus 1 1, because they are connected. So let us do for, and velocity u11. So we will do it for theta 1 1. So this should be, strictly speaking, is called p, but I use the same. So I have to go like that, counterclockwise, and I will just not go into. So n theta. So this is a nonlinear term coming from these two terms. Okay, and the linear term uz will be, is non-zero now for u11, and you can see it from the table itself. I do not really need Kriya Haring for this. So this is u11 by I. From the table you can pick it, and this term, what is k prime square? 1 plus 1, which is 2. So this is k prime square 2, and this theta 1 1 by I. Okay. Now n theta you can compute. I mean, so this is 2I. So my n theta is 2I u11 theta 0 2. Okay. So the I goes, and so there is a minus 2 this one. Oops. So, the next term is this one. So, this is my real equation which tells you the time dependence of theta 1 1 dot, okay, and this is a nonlinear term. If nonlinear term is off, then I will get u 1 1 these two together. In fact, if you look at instability equation, you will basically get these two for this k choice of kx and kz. So, term of nonlinearity I should recover, and I urge you to kind of double check this very useful thing to check your calculation. Should get exactly the same equation what we got for instability calculation. Okay. So, the third equation for the velocity field in Lorentz. So, we had theta 1 1, theta 0 2. The third equation is for the velocity field u 1 1. So, I am taking this 1 1 k prime I am shifting around, okay, right now is 1 1. So, to derive this I take dot product of this with E2 k prime dot. So, E2 is in that direction. You take a dot product of this. So, this will give us d by dt of u2. Now, nonlinear term you can work out this, I will not do it here, it is 0. In fact, it is quite easy to see that for this velocity field of this multiplied by velocity of field of this. So, there are two velocity minus p minus q. So, velocity field of 0 2 is 0, 0 minus 2 and this is minus 2, that is 0. So, this term goes away. Okay. Now, if a dot product of this with E2, what will I get? K dot E2 k prime is this k prime, that is 0, right. K prime and k prime is in that direction. So, k prime dot E2 k is 0. So, dot product gives you 0. Okay. So, I should say the dot product, not itself, dot product is 0. Now, actually my bracket should be here. Okay. So, what is E2k multiplied by that? So, E2 is in that direction. So, this angle is what we got, right, z cap is upward. So, sin 135, right. So, this angle. So, this will be RAPR. Right now, these angles are 45 each. So, this is sin 45 kz. Well, sin 45 times k, or in fact, it is better to just write kz, right. Let us write no. This is a unit vector and this is also unit vector. So, there is no k involved in this, just angle between the two, sine of that is 1 by root 2 dot product, no, sine cos of 135, the minus sign will come, not sine, cos of 135. So, this will give us 1 by root 2, and the right hand side will, the other term is minus k squared u2 of k. So, this should be of k prime. I have been a bit lazy. Okay. So, I will not do this step. So, now u2 you have to replace in terms of u11 by root 2. Remember, we have this one. So, you substitute it here, you will get this equation. Okay. So, this is how we derive equation for u2 of u11, basically u11. So, these are the three equations. We have theta, one equation for theta and two equations for temperature, theta 0 2 and theta 1 1. So, the three equations are summarized here. So, I just rewrote them here. So, u11 has no nonlinear term, theta 11 has nonlinear term and theta 0 2 has nonlinear term. If I turn off the nonlinearity, then theta 0 2 goes to 0 and these two are coupled. In fact, we will get exactly same equation without with nonlinearity turned off. Okay. Now, can we estimate Rayleigh critical as 8 from linear approximation of these two equations, the top? It should come, no, it better be. So, So, linear stability will give you that u11 dot must be 0 and theta 11 dot is 0, no growth, neutral mode means no growth. So, that gives you from the first equation it gives you, so PR cancels. So, Rayleigh theta 11 equal to minus 4 u11, but what is u11 from here is minus 2 theta 11. So, minus minus becomes plus 8 theta 11. So, Rayleigh critical is 8. Okay. So, it better come that way. So, that is what we get. So, it is consistent. Now, so this is one part. Now, second part is let us look at the fixed point of the full nonlinear equation. Fixed point means, what is the fixed point? Is I set the time derivative to 0, d by dt is 0. So, this is called fixed point, things do not change with time. It could be stable or unstable, but so one fixed point is all modes are 0, right, is that correct? If I set theta 11 0, u11 0, theta 0 0, so that is the fixed point. So, that is the conduction state, no convection. Okay, so that is a solution, but there are in fact two more solutions. Okay, so what are the two solutions? Now, I will just, so how will it solve this? This is, if you have done Lorentz equation before, is just straightforward. You have 3 equations and 3 unknowns, and you can solve it. I mean, this one gives a relationship between u1 1. So, this is straightforward. Okay, I mean you can do it. I will write the solution. The solutions are here. Now, if this is a plus, then u11 should be minus. No, actually, yeah. So, no, theta, the plus sign. I am slightly. What is the relationship between plus? Okay, plus 1 plus goes with plus, or no, they are opposite sign. You see, theta 11 and u11 must be opposite sign. So, this should be minus plus. Okay, so minus plus. So, these are the solutions. Now, all 3 modes are non-zero, but there are 2 choices. If the theta 1 is plus, then I plus minus and minus plus. Lorentz, by just putting a minus sign in one of the terms, he gets plus plus for both and minus minus, 2 solutions. Okay, yeah, good point. Small r is Rayleigh by Rayleigh critical. Okay, so these solutions are meaningful only for r greater than 1, greater than equal to 1. Okay, if r equal to 1, they become 0. So, r equal to 1 is a transition point, and that is indeed the case, because Rayleigh by Rayleigh critical is 1. So, if I plot them as function of Rayleigh, a small r, let us plot as function of small r, I get this. So, this small r, and so this is small r equal to 1, and the y axis I can choose to be theta 11 if you like. So, it is specially going as, so Rayleigh is approximately 8, this number is approximately 8. When I increase small r, of course Rayleigh also changes, but near the onset this is constant, this is 8. So, it is approximated as square root r minus 1 apart from prefactors, and minus square root minus 1. So, there are 2 solutions, and before the onset I get 0 solution. So, I should say there is one solution is all are zeros, theta use 0. So, this is conduction solution, that is also a solution. So, this was before the convection starts, and this is after the convection starts, either plus or minus, and the 0 solution still exists when small r is big greater than 1, but the 0 solution always exists, but they become, you can do the eigenvalue analysis and you can show that they are unstable. How will you show it is unstable? So, if I plug, so you look at the eigenvalues, just put the values of 0 0 0 and look at the eigenvalues, they will be all positive part, real part will be positive. So, they simply grow from there, but this is stable. So, this will just converge here. So, you can look at the eigenvalues and that will tell you that stable solution or unstable solution, exactly like what we did for linear stability. Linearize around the solution. You understand me or not understand me? Okay, so I will give you a simple example. So, let us do x dot equal to alpha x. So, it has solution x equal to 0, fixed point solution. So, for is it stable or unstable, this solution? Depends on alpha. So, x equal to 0 is the solution. If alpha is negative, then it comes to x equal to 0. If alpha is positive, it runs away. So, alpha is like eigenvalue, in fact is eigenvalue. So, you see the eigenvalue of the solution, well of your not eigenvalue of the matrix of your equation, linear equation. If it is negative, then it will be stable. If it is positive, then it will go away. Okay. So, this is for a simple equation. Now, you can also do for matrix. We did for linear analysis, but suppose I have non-linear equation, then what do I do? So, then you write it as x, let us say I write it as x square. So, let us do for 1D solution. So what is my solution? X equal to 0 and x equal to alpha, two solutions, is that correct? Yeah. Now, which is stable and which is unstable? Now, 0 solution and alpha is solution. So, let us imagine alpha is positive here, okay, alpha. So, x equal to 0 is a stable solution or unstable solution? So, you linearize around x equal to 0. So, if I have small perturbation around x equal to 0, will it grow or will my x grow or not? So, for small alpha x means this can be dropped. So, this dropped. So, my x will grow, alpha positive. So, it will grow from here and it will grow in that side as well. But what happens for this solution? So, you have to now do perturbation. So, how will I do the perturbation? So, the best thing to do is, for first time you should do very like like a stupid guy. So, you just put in from basic x prime is equal, x prime is x equal to x prime plus alpha, x prime is a small number. If you plug it in here, what will I get? X prime dot equal to minus alpha x prime plus alpha minus x prime square, x square. So, which is x prime square plus 2 alpha x plus alpha square. So, I am doing a lot of algebra, but so x prime square can be dropped. So, this is gone. So, I get minus 3 alpha x prime, minus 3 alpha x prime, and alpha square will cancel. Is a minus sign or it is a plus sign here, this plus sign here, plus sign here, okay. So, I am sorry, I made a mistake. So, alpha square will cancel and I get minus alpha x prime. Now, so alpha is positive, so that means it will be stable, x prime will go to 0. So, this is a stable solution. So, it will come like that. So, that is how you linearize around the solution, okay. And this is for 1D equation, but you can also do for matrices. For matrices, you need to look at the eigenvalues. Okay. So, the summary of the story is that for r less than 1, this is stable solution is all the u11, theta 11, u0 to 0, theta 0 to 0. For r greater than 1, I get these non-zero solutions, and they are, so at least the u11 and theta 11 go as square root r minus 1, and this is called pitchfork bifurcation. So, my road is bifurcating. Bifurcation means the road hits some dead end, well not a dead end, hits a bifurcation. So, you get new roads. So, the amplitude of the roads are this variable is square root r minus 1. Okay. It has a name pitchfork, and the solution remain real. Now, the theta 02 is interesting. So, it goes with half r minus 1. Okay. Now, I will not tell you right now, but you can do some more stuff. So, theta 02 is not following a square root r minus 1. It is a different solution, and it is following this. So, what is the summary? What is the upshot? So, the growth has stopped. No, and so what was linear stability telling you that theta 11 should have been growing, no, I mean indefinitely, but in this solution you see that it does not grow. For given r, I know where theta 11 should go toward. It will grow in the beginning, but it will saturate to a value. So, in convection these rolls are going around like this, but the amplitude gets fixed to this value of the amplitude. It is not increasing anymore. So, the velocity field is, well, velocity field is function of x, but it is not function of time. It is steady roll. Temperature field is also steady. So, what we have achieved is that we have suppressed the growth by nonlinear interaction. So, theta 002 took that energy, and it in fact is happily sitting with the constant value. It also gets a value, and theta 002 took that energy. Now, we will study how the energy is transferred, which I have not done it yet, but you can compute how much energy is being transferred per unit time. And study means if I get some energy, well, there are now if you look at energy stuff. So, any mode gets energy from thermal convection, you know. It can lose energy by nonlinear transfer, it gives to somebody, and it can lose by dissipation. So, fixed stable solution means they all balance. So, without nonlinearity it was getting, and it was more than dissipation. So, it was trying to grow fast, but because of this nonlinear interaction, it is the balance is exactly the nonlinear interaction which goes there. Okay. So, that is a fixed point solution. Now, so Lorentz equation, if you increase a small r more, I mean further, then it becomes chaotic. At some point it comes here and it becomes chaotic. So, 24 small r is some 24 or 25, it becomes chaotic. So, there is some another, so this solution will not, if we increase r, then the solution will not remain stable. So, there is another bifurcation, in fact here is called Hopf bifurcation, and that kills it. So, one bifurcation does not mean it will stay there forever. So, if you increase the parameters, there will be more dynamics. Okay, so this Lorentz equation we can, okay, so this simplest equation which gives you saturation. So, I need to I had to include only one mode, 02 mode. I could include more modes. In fact, we have done some, well, there are many people who have done work with including more modes, and more modes if you put, then you get different patterns. So, in the book you will find an example where it is a 3D structure which has 101, 011, 112 mode. You can see they are forming a triad. If you want the sum to be 0 is like this. So, 3 velocity, 3 temperature and 002. So, these are 7 mode model. So, the 7 modes. So, these are 3D structure, so which she is studying, and the 3D structure has rolls which are like this. So, one roll is going like this, other roll is going like this, there is competition and things like that. So, maybe time permitting we will discuss it, but we can make complex set of dynamics with these rolls. Okay. These rows give very nice pattern, square pattern. One more point I want to say is that Lorentz equation is valid for large Prandtl number. Why large Prandtl number? Because you can see the viscous term is dominant and nonlinear term for velocity field is 0. So, when does nonlinear term become 0 for velocity field? When it is a laminar flow, no, everybody knows fluid dynamics. If viscosity term is too large, then nonlinear term can be dropped. So, nonlinear term is dropped, so it is basically valid for large Prandtl number, large viscosity, laminar flows. So, these are basically good for Prandtl number 10 in near the onset. But if Prandtl number is small, so let us say 0.10⁻³ then nonlinear term will grow, will come in the velocity field. So, u dot rad u cannot be dropped. So, there will be some perturbation and u dot rad u will become important. So, that is why this Lorentz equation is not very good model for small Prandtl number. Small Prandtl number I need nonlinearity in the velocity field, and for temperature field we may be able to ignore the nonlinear term. So, we have to go other way around. Here we suppress the nonlinear term in the velocity field and kept the nonlinear term in the temperature equation, but we will have to go other way around for small Prandtl number. We keep the nonlinear term in the velocity field and suppress the other ways. So, I will give one project in that direction, and you can see these patterns which I was telling is like wavy like pattern. So, we can really do lot of stuff once you put in the nonlinearity. So, interaction starts coming into play, patterns, chaos, all of it will come. Okay, so this is about it. Okay, thank you.